This is an introduction to the mathematics governing acceleration. In this video, we will focus on constant acceleration. Acceleration is defined as the change in velocity over time. Velocity is a vector, and so is acceleration. If there is a change in either the magnitude or the direction of velocity, there is acceleration. The units are meters per second squared. If the problem specifies constant acceleration, then through any time interval, the change in velocity must be the same. This includes the direction as well. The direction of acceleration always points in the direction of the change in velocity. Be warned that negative acceleration does not mean that an object is slowing down. As a vector, the negative sign means opposite the direction of the coordinate system you set up. In these examples, the change in velocity and hence acceleration point towards negative coordinates. But because the object was already moving in the negative coordinate, and the acceleration is towards the same direction, the object is speeding up. The rule of thumb is that if the initial velocity vector agrees in sign with the acceleration vector, the object is speeding up. If the signs are opposite, then the object is slowing down. Because we are now considering constant acceleration only, all motion is along a single straight line. You can then set up your coordinate system along that single line. Here are the equations to be used under assumption of constant acceleration. They relate change in position, change in velocity, acceleration, and time. For those interested in the derivation of these equations, please follow the rest of the video. We start with the definition of acceleration. Under constant acceleration, the acceleration at any given time is the same as average acceleration, which is defined as the change in velocity over change in time. For the rest of the derivation, we will choose our initial time as our reference 0 time. Hence, to get our first kinematic equation for constant acceleration, we simply rearrange the equation for average acceleration. This can be used for problems that relate final velocity, initial velocity, acceleration, and time. If any of them is unknown, we need to know the other three. Now let's derive the equation that relates the change in position, initial velocity, acceleration, and time. We start with the definition of average velocity. Average velocity is the change in position, also known as displacement, over time. Under constant acceleration only, the average velocity can also be found as the arithmetic mean of the final velocity and the initial velocity. We can combine the two expressions and substitute in for final velocity from equation 1. The rest is just simplification and rearranging. This equation can now be used to find change in position without regard to knowledge of final velocity. The final kinematic equation is necessary for problems where time is not known nor is important. We start yet again with the expressions for average velocity, which then we cross-multiply. This time, we substitute in from equation 1, but rearrange for time. The rest is just multiplication, simplification, and rearranging. Use these equations for kinematic quantities. In choosing which equation to use, consider first what quantity do you want to find. Then eliminate equations based on what is given. For example, if you need to find a change in position, but the time is not known, then equation 3 is the one that needs to be used. Aside from the algebra, also never forget to draw a vector diagram to be able to describe what is going on.